Good morning to all of you. I will be discussing the topics like introduction to facts. Then we will do for transmission line parameter calculation for IEEE bus, which we require for inserting in the MATLAB Simulink model. Then we will do the load flow calculation in MATLAB. Then SVC, its introduction, its MATLAB simulation and its characteristics. STATCOM and similarly TCSC. Now, coming to the present scenario of electrical transmission, as you are all aware that economic development of the country is depicted by the growth in its electric sector. Also, per capita energy consumption is one of the indicators of its development. So, there is continuous increase in electricity demand, and there is a necessity as the demand increases, there is always necessity to see about its quality and reliability. Also, renewable energy sources are increasing day by day. Their interconnection to the main grid has become a very problem. Every time it is not possible to construct new transmission line because it is not feasible for land and permit granting and environmental crisis. So because of this, there is no optimal utilization of transmission line assets. To such and many problems, facts is the solution. If facts are used in the interconnecting or for reactive power compensation, many of the problems can be solved. So what are facts devices? It is nothing but large application of power electronics. It is real-time based, computer controlled, compensators and controllers. Also, they provide cost-effective, high-tech solution to the power transmission. The era of facts has triggered with the development of new solid-state electrical switching devices. Facts are usually connected on HV side of transmission line. As you know, facts have immense benefits. It controls magnitude and direction of the power flow. It overcomes specific limitation of line. Suppose we want to maintain the voltage profile or we want to control the power transmitted, facts can be best option. It improves transient stability limit. During dynamic response, you will get with facts good dynamic response. It enhances grid stability. It provides secure line connections. Also, it facilitates interconnection of renewable and distributed generation. Reactive power compensation is the most effective, which can be seen by the facts. It also mitigates subsynchronous resonance, enhances system damping, and reduces instances of blackout or cascading outage. So, the principles on which all the facts devices work are shown here. This is the first diagram shows that power system, that is sending end voltage E1, receiving end voltage E2, shown by the drop or voltage across the transmission line, and this is the current flowing. Current through the transmission line and voltage across the transmission line are parallel or perpendicular to each other. Also, you know that power transmitted through transmission line is product of the sending end voltage, receiving end voltage, angle, sine of angle, and divided by the impedance of the transmission line. So this also reactive power is given by the difference of the voltages multiplied by its sending end voltage and cos of the angle between the sending end and receiving end divided by the x. This you are aware with. Now this is the general representation of power flow transmission line voltages. Now when we want to change power, either reactive or real, facts devices help in this way. That is, suppose you increase the or decrease the impedance of the transmission line, power flow will be controlled. So this principle of changing the impedance is used in TCSC, that is, or impedance type impedance type fax devices. Now this is the diagram showing two voltages, that is sending and receiving end. If you increase or if you inject voltage in series with the transmission line, that will increase the current flowing, which will increase the transmitted active power over the line. This principle is used in series connected fax devices, that is SSSC. If sending end voltage and receiving end voltage, either of them is boosted is with voltage, if you add voltage, if you boost the voltage at either of the ends of either sending end or receiving end, that will change the magnitude of the voltage, and which will in turn affect reactive power flowing through the line. This principle is used in STATCOM. That is, you can change voltage profile by adding, which will give reactive power flow control. These two principles are used where there is also control of power, active power as well as reactive power. So this principle is used in UPFC. Before going to the actual fax controller, I would like to mention the importance of reactive power in the transmission line. See, these two figures indicate that the horse is pulling the boat in a canal. His objective is to move the boat straightly and smoothly. His objective is as if active power. But since the horse and boat are not in a straight line, the rudder has to support the motion. So that is reactive power. That is, without the help of rudder support, the boat cannot be navigated in a straight line. So that means without this support provided by the rudder is as if reactive power. That means without reactive power, horse cannot pull the boat. That is, there cannot be flow of active power. So reactive power is a must for transmitting active power. Also, there should be proper balance between the active power and reactive power. You know, reactive power flows from higher magnitude to lower magnitude, whereas active power flows from leading angle to lagging angle. So reactive power, which is a part and parcel of transmission, you cannot avoid, but it produces losses, but it is a compulsory, it is a must, it should be in balance, and without which you cannot transmit active power. Now this I will be showing with the diagram that how reactive power affects, and if it is required in excess, that is, if it is not balanced, it will lead to voltage instability, which may be leading to even blackouts. Now this is a healthy network which is shown over here with 4 generators, lines, loads. Suppose there is a sudden increase in reactive power or sudden increase in the load, and it is also followed by a contingency, like one of the generators is taken out of service, the lines connecting the generator will get overloaded. They are shown by this red diagram lines. With this overload and with this one of the generator out of service, one of the lines connecting the generator and the load gets disconnected. So this EHV lines, once it is disconnected, the load of this is transferred to the other lines, which get more overloaded because of the reactive power loss occurring in the lines. There is a tremendous overload, which will lead to voltages at the buses to a reduced value. The voltage at the buses gets reduced because there is a much drop occurring in the line. And because of that, the load connected at the bus gets disconnected as the under voltage relays operate, and they disconnect the load. With this disconnection, the system tries to become stabilized. The generators, they generate reactive power controlling their excitation system, and that generated reactive power will now flow through the lines, which will produce again the drop across the lines. Because when the reactive power flows through the line, it creates, or there occurs, loss in the inductance part of the transmission system, that is lines, transformers, etc. So because of this, there is a much loss occurring, the lines get still overloaded, and with this the generator 2, that is not able to generate the required amount of reactive power because it hits its uh, field excitation or field current limit, and at the reduced voltage, armature current increases, which further limits its reactive generation. And with this, there occurs the voltage at the generator 2 is reduced, which leads to hits its limit, and the um, reactive power, its share is transferred to the next generator, which also has its limit. And again, with this, there is a cascading, all the generators get tripped, and the load becomes tripped, and there is a complete blackout. This was the same scenario which we have experienced in 2012, where most of the north 22 states from the north India are black. There was blackout. Even some 300 million and 620 million people were uh, affected. This was only due to the same reasons that we have discussed now. That is, one of the lines was stripped, one of the generator was stripped, the other were overloaded, and one by one, all the generators, they were tripped. So, if there would have been facts, or facts is the solution for tripping or avoiding such blackouts. If there would have been facts, if there have been sufficient reactive power compensators installed in the lines, they would have met the increased load, and there would not have been loss in the transmission line, there would not, and all this that we have discussed. So FACTS controllers are basically classified as variable impedance type, and other is variable voltage source converter type. In variable impedance, we have SVC, that is static VAR compensators, which include, depending on the um, conventional components used, they are classified. That is, they can, but conventional components like inductance and capacitor banks are used, but they are many times controlled by uh, semiconductor devices. They are in many places, even they are right now installed with mechanical switches, but mechanical switches has got its own disadvantages like speed and repeatability, which can be overcome by the semiconductor switches. So SVC is one of the variable impedance type FACTS controller which is connected in shunt. Then series connected are thyristor controlled series capacitors or thyristor switched series capacitors, and thyristor switched series reactors, and phase shifting transformers. In voltage source converters type of FACTS, there are no conventional equipments used like inductance and capacitor banks. Their effect of leading or lagging current is produced by the semiconductor devices, such that they will produce, or their phase shift will be such that it is as if current is leading the voltage, that is capacity or lagging effect. So instead of using bulky, big, which are very difficult for installation also, such components, the effect is produced by converters and inverter action, which will give the same effect as that of the conventional compensating equipments. So STATCOM is connected in shunt, series connected shunt also are there. UPFC has advantages of both shunt as well as series connected facts. And IPFC, it is a series connected voltage source converter. So again, here I have shown the classification according to the type of connection. Now we will come to the actual transmission lines and how their simulation is done in the MATLAB and their uh, load flow calculation. Now when you search for any data for IEEE standard bus, suppose you type on Google datasheet for IEEE 5 bus network or IEEE 14 bus, whatever you want. So when you type that and when you get in the datasheet resistance, reactance and susceptance in per unit value, that is datasheet of IEEE standard bus includes resistance, reactance and susceptance in per unit value. But in Simulink model, these values need to be transferred in actual values. And values are also of resistance. Instead of reactance, it is inductance. Instead of susceptance, it is capacitance. And also you have to enter the length of the line, because the line has some length which is given. So if you download that, you will get like from bus to bus, that is from bus 1 to bus 2, or from resistance which has the resistance of 0.02 per unit, reactance is 0.06, conductance is G is 0, and susceptance many times it is half B by 2 is given, or sometimes it is total susceptance of the line is given. So you just see carefully whether it is B by 2 given or B is susceptance of the line is given. So this is I have taken for 5 IEEE bus which has 7 lines. Now this is, can you see this? This is the block diagram for 3-phase pi section line for MATLAB Simulink model. Here you can see, can you see this positive or zero sequence resistance which is in ohms per kilometer? That means you have to enter positive sequence of resistance for the transmission line where it should be written actual value of ohms per kilometer. Then positive sequence and zero sequence of inductance in Henry per kilometer. And positive and zero sequence capacitance is farads per kilometer. So these values we need to calculate, because in the datasheet which we have downloaded or which we have is in per unit. So that per unit should be converted to actual value, and the values per kilometer should be entered. Now as you know, per unit calculation, that there should be some base value for the voltage, there should be MVA for the voltage. So here we have selected 230 kilovolts as base value and 100 MVA as the base value, that is MVA value. Now in our data sheet, the resistance is 0.05, X is 0.06 pu and susceptance is 0.06. Now first we should calculate length, because we want value per kilometer. So length of the line can be calculated by the formula under root xb upon 2 pi f into velocity of light in kilometers per second. Because we want the length in kilometers, we have taken this unit. So length is equal to whatever values we have for x and b, we have substituted here, and we get the length of the transmission line from bus 1 to 2 as 47 kilometer. Now we want to calculate resistance of the line. So you know that Z base is equal to R base, which is also equal to X base. R actual is R base into PU per unit. So R base is equal to, you know the formula for calculating base values as base voltage square upon power, MVA. So with that you get resistance of base value resistance is 529 and actual value of resistance is per unit into base. So it comes to be 10.58. Now we want it in ohms per kilometer. So it is divided by the kilometer that we have calculated, which is 47 kilometers. So R1 is the actual value of the transmission line in ohms per kilometer, and this is zero sequence resistance, which is 3 times the positive sequence value. Are you getting it? Am I going too fast? Okay. Positive and zero. Similarly, we have to calculate for positive and zero sequence inductance. Again, actual value of inductance is base into per unit value. Base value is 529 as we have calculated. X actual, that is reactive inductance. Inductive reactance is per unit value, we know it is 31.974, but it is reactance. We want the values in inductance because we have seen that in pi section there is inductance per Henry per kilometer we require. So we divide it by 2 pi f, you get L actual, that is inductive value, inductance value in actual, and then you divide by length, you will get Henry per kilometer, which we want to enter in the pi section model of Simulink. See, once you know resistance value calculation, you can do it is same as for inductance. Similarly, for susceptance, you know, instead of now here base impedance, we have to calculate base admittance. From base admittance, that is the even formula will be reversed, that is MVA upon KV square, which will give base value of susceptance. From there, you can calculate capacitor actual. From capacitance value, you can get farads per kilometer, that is divided by the length of the line. So these parameters we have entered in the pi section model of the MDL file or MATLAB file. Here we have written resistance, inductance and capacitance value with their proper units and length of the line. So with this, now just we will see how load flow is to be done, then we will go to actual MATLAB environment and we will simulate the model. So before simulation, you convert all the per unit values of transmission line parameters into actual values, because in Simulink model we want actual value per kilometer. Then convert like generation, load and maximum and minimum value of reactive power limit for PV generator to actual values, because when generation is given, generation load are also given in per unit. Suppose it is given as 0.5 megawatt per unit, you have to convert as you have taken the base value for MVA. If you take base MVA as 100 MVA, then 5 into 100 will give 500. So you have to convert actual values of load, generation and the limit for reactive power for PV generation or for PV generator. So that you have to enter in the Simulink model. Now, in case of generator, you have to mention the generator type. That is which type of generator it is, whether it is a swing bus or whether it is a swing generator or whether it is a PV generator. In case of swing generator, voltage and angle are constant, they are fixed, they are specified. In case of PV generation, active power and voltage are specified. The other two quantities like angle and reactive power, that will be calculated by the load flow. Then in case of load, see all this we have to connect. That is why I have mentioned here. So you have to mention that in every respective block. In case of load, you have to mention whether it is PQ or constant Z. Then connect load flow bus where voltage and angle is to be calculated. So this is orange color bus is shown. This will, when you connect in the this in the model, this will give the indication that you have to calculate the load flow at this particular point. And once the load flow is calculated, the values of the voltage, this is the value of voltage, and at what angle it is shown. This 0.9842 is voltage after load flow calculation, and this is the angle at which this voltage is there. So it is given. This is the location. This is the base voltage that we have entered. Report of the load flow is available. We will see that also, which will give how much iterations it has taken and how it is completed. So before going to MATLAB model, I am showing you, this is the generator. These are the two generators, orange color. These are the green color loads. These are the transmission lines. All the parameters entered here are as per the calculation that we have discussed. This black indicates VI measurement. That is what is the measurement at this particular bus, and that you can see voltage and current measurement in a scope. Now we will go to MATLAB environment where this model is built. Here, can you see this? This is three-phase source. Instead of generator, we have taken source. Can you see this? Then in load flow, we have mentioned here swing bus. Also, when it is a voltage source, this is a PV generator. Instead of that, again one voltage source is taken. Here values are mentioned. Base value is mentioned basically, and here the generator type is mentioned, and it's active in PV. As we have discussed, active power is known. So 40 e raised to 6, this is the actual value. It is 0.4 pu whenever you get the data sheet, but it is converted to actual value. And this is also the minimum reactive power limit. This also we have entered because it is a PV bus. Then, as we have discussed, this is all transmission line that we have calculated. All the parameters are entered, like 47 kilometer was the length. These are the resistance, reactance. Zero sequence resistance is 3 times positive sequence. Likewise for inductance and even for capacitance is thrice the positive sequence. If you want measurement at this bus, here voltage measurement phase to phase, use label, that we have used the label. Then it's V4 is the signal, current is also we want to measure, so use label. Then it's I4 is the signal, and current value should be in per unit. So with this, then we have taken one power GUI, which will connect the Simulink blocks and the SimPower system blocks, and this will give the load flow. When you double click this, here there is a load flow option. it is processing. Now this is the, here you can see compute. So this will compute the load flow for the IEEE 5 bus network with the values that we have entered for the transmission line parameters and voltage generators and loads. So once you compute and then you say apply, apply will be apply will make all it will reflect it, the values of voltage and angles will be reflected on the load flow buses. Okay, then here it calculates the power, that is first generator, which we have defined as swing, has generated 131 active power in megawatts and reactive power of 90.97 megawatt MVAR. Likewise, it has calculated all the generation and loads at the buses and the angles. These are the angles at various buses. So bus 1 has angle which is the swing bus, which we have specified as 1.06 because it is a swing bus. It is the angle is at 0. Then at PV bus, this is the calculated voltage and this is the angle. And if you want report of this, you can take its report in some other file and save that report. Now I have saved it. I am saving it on report will indicate how many iterations are required to calculate the flow. And what are the total losses occurring in the transmission line, and everything will be included in the report. Do you have any problem right up to load flow of 5 IEEE 5 bus? All centers.
Hello.
Huh?
Ma'am, in swing bus, it is showing 1.06. Generally, 1 at an angle 0 is voltage. And second doubt is magnitude. All buses are having 230 volts.
Yeah. It is showing everything in per unit value because we have specified as base value as 230 volts. And we have used the labels which should indicate that it should be in per unit. So it is not showing the actual value. And even in load flow, it is always per unit values are given because the values are too big to handle.
Ma'am, can you just go to that result of load flow?
Okay. Yeah.
Yes. Here in voltage KV, all are shown as 230 volts.
This is we have entered. This is we have entered as base values.
Okay.
And these are the calculated values.
Okay. That P reference is 1.06.
Yeah. This is for swing bus. Voltage is always constant.
Yes.
We specify that how much we want. So
Okay.
it is that. And in PV bus also voltage is same 1 volt as we mentioned.
Okay.
And these are the 3 values which are calculated by load flow.
These are PQ buses. Fine. Bus number 3, 4, and 5 are PQ buses. Okay.
Yeah.
Thank you, ma'am.
And this is the swing bus calculates or it generates whatever is actually required by the system, which is not defined by any other generator, is calculated or is generated by the swing bus, which is generally the largest of all the generators of the system.
Yes, ma'am. Okay. Thank you. Thank you very much.
And if you simulate this, and if you want to see the waveform, here these from blocks are used. Here it is, I have taken for 5 bus. That will give the value for, see here I have taken infinite time. So because of that, you can see the continuously the waveforms. If I take for few seconds, it will show you 3-phase voltage in PU value and whatever current is at that bus in PU values, because we have specified volt in the VI, the measurement to be in PU per unit. Use label, here current is in per unit. Here also measurement of voltage, use label. If I take it per unit, it will give in per unit. Okay, should we go for SVC? ठीक है? If there is any query, you can ask for load flow, and for this model calculation and load flow. Load flow mainly coming back to our presentation, this we have done. Errors that are occur in load flow are usually model should contain at least one swing bus. That is very general. That is, if there is no swing bus, you will not get load flow. It is, so you should check every generator type. There is a one parameter for generator type where we have entered swing bus and PV bus, that you should check. That will give, if you correct that, you will, this error will be eliminated. Or sometimes it finds that load flow does not converge in whatever iterations you have mentioned, it does not converge. In that case, you have to check all the parameters of transmission lines, even for parameters for active reactive power and its limit. It is because in no, load flow is calculated by the MATLAB by Newton-Raphson method. In Newton-Raphson, if the Jacobian matrix is having sparse or it is having very small value, it will not converge because it will not calculate the values which will converge. So the state variable matrix form will not be converging. So if the does not converge error comes, you should again check all the values that you have entered for the model. Okay, should we go for SVC? See, this was the first basic uncompensated transmission grid we have seen. Like this, you can also find the load flow for 14 bus. Once you know the method of calculation for PU to actual values and how to enter the generator type and the loads in actual values. Now, once you get successfully the load flow, you can connect one by one compensating devices in the power system. So, and with this compensating device, then you can check if the load is increased, how the compensating fact device will behave. If the load is decreased, how the reactive power or other parameters can be, depending on the type of the controller or depending on type of even settings of the reference values, you can check those characteristics. Now to start with, you know, SVC is a shunt connected FACTS device. It has conventional reactive power compensating devices like inductance and capacitance, but they are switched on and off with the help of semiconducting devices like IGBTs and not by the mechanical switches. So SVC injects or absorbs reactive power to regulate voltage at a given bus against load variation. If load increases, you have to boost the reactive power or you have to boost the voltage. So that is as if injecting. If load decreases, the voltage should be lowered at the receiving end, which means it should absorb the reactive power. So for that, thyristor switched capacitors are used. They are capacitor banks, but they are switched by thyristors in case of heavy load to maintain bus voltage, and thyristor controlled reactor. See, capacitors are always switched. You cannot control capacitor simply. If there is a capacitor bank, you cannot control. You can either make it on or off. But if it is a thyristor, if it is a reactor, you can control its impedance by varying the delay angle. Are you getting it? Capacitor banks or capacitors can either be switched in and out. They cannot be controlled, whereas reactors can be controlled by changing the delay angle, firing angle. This is due to the charge that is accumulated or that exists on the capacitors. You cannot switch on capacitor just like that and make it on. It should be switched on at such a point where there will be minimum transients produced. So SVC injects, so reactor absorb reactive power, thyristor controlled reactors absorb reactive power from the line in case of light load to maintain bus voltage. Also, SVC injects controlled capacitive or inductive current so as to maintain or control mainly the bus voltage. It is mainly used for voltage profile maintenance. SVC are, in a world, there are more than 800 SVCs connected. These are the most simplest, most very effective controllers normally used. So, and these are very, as compared to other controllers, are having less cost. So their number in the world is maximum and their maintenance is also less. So SVC improves transmission power transfer capability to enhance power performance. So this is the SVC. Oh, this coupling transformer has shifted. So this is the coupling transformer which is just shifted from this line. Are you getting it? So here there is a reactor which is controlled by the thyristors, and 3 are the thyristor switched capacitor banks. This is the general representation. Then see, if you see to this slide, it is parallel combination of three banks of capacitors and reactor. So current in the reactor can be controlled from maximum to 0 by method of firing angle. If firing angle is 0, that means no delay. It is as if you have switched the reactor without any. If you give some delay, current will be reduced, which will be because its conduction is reduced. So current carried by the reactor will reduce, which is as if it has high impedance. Current is reduced, it means it is taking high ho gaya. So it is as if introducing high reactor in the SVC. that will it will absorb power. So once you know the concept of inductance and capacitance and they are connected in parallel, you can calculate its equivalent susceptance, and accordingly you can think of designing for how much it will supply or how much it will generate the reactive power. Reactive power, you know, is supplied or given either by capacitors and reactors. So susceptance of is or a reactor or inductive reactance. Now since it is connected in parallel, it is susceptance. It is a function of delay angle alpha, which is given by 1 upon omega L, 1 minus 2 alpha by pi minus sine 2 alpha by pi. Since closure of thyristor wall is delayed with respect to peak of applied voltage, because it is inductor, its characteristics is it lags current by 90 degrees. So when the voltage is at peak, current will be 0. 90 degrees lagging means when the voltage is at peak value, current through the inductor will be 90 degrees lagging, so it will be at 0. So amplitude of fundamental reactor current will be given by voltage upon the impedance of the reactor, or you can say susceptance, voltage into susceptance. Firing angle control is not applicable in case of capacitor, as we have discussed. It should be switched on, capacitor bank should be switched on and off when there is minimum transient, or in other case you can say minimum voltage across the switches means semiconductor devices. So TC thyristor switched capacitor represents simple capacitive admittance which is either connected or disconnected. Now this is the general controller used in SVC, that is, this represents the power system. It is high voltage side, primary side. Step down transformer is used. This is the secondary side. From primary side, voltage measurements are done because we want to control the primary voltage basically. That is compared with reference. The error is given and it is voltage regulator. Voltage regulator will calculate how much susceptance is required to provide the necessary voltage. That susceptance, which components will, because we have 3 capacitor banks and 1 reactor, so which component should be made on and off to meet this susceptance. Accordingly, it will give pulses to the capacitor and firing angle to the reactor. And with the help of PLL blocks which synchronizes with the, which give the pulses so as the voltage output will be synchronized with the line, it gives pulses to the switch capacitor to switch the capacitor and firing angle to give the firing delay to the reactor. So it is very simple. Voltage measurement is done. It is compared with reference. How much voltage is to be supplied by SVC is calculated. How much should be the susceptance to provide that much voltage, that is calculated. Which components, which banks and which should be on and off, that is decided. And how much should be the delay angle for the reactor, that is calculated. Because when you switch on a capacitor bank, though the requirement is less, but whatever capacitor bank is providing, that will be generated. But the surplus capacitive reactive power is cancelled by the reactor. Because this you will come to know when we will simulate one circuit. So it is written the same thing. whatever functions for every block we have discussed. This is the controller in MATLAB. This is already a developed model. Here it is the measurement system. Here it is the voltage regulator, which calculates the susceptance. Then susceptance value is given to distribution unit, which decides which units should be made on. Accordingly, pulses are generated, which will be given to the capacitor banks, and firing angle is given to the thyristor controlled reactor. This is the circuit. We will see that here it is the voltage source. This represents transmission line. This is the load. This is the entire SVC, which is connected in parallel in shunt through this step down transformer. And this is the controller, which takes input only from primary voltage and secondary voltage and gives pulses to the capacitor bank and firing angle to the thyristor controlled reactor. Before going to actual MATLAB circuit, we will see what values are to be entered. In programmable voltage source, you need to enter the values of voltages with respect to time, because this gives variation in voltages so that you can see the dynamic response. Then there is RL branch, which serves the purpose of transmission line. Then there is a step down transformer. So you need to enter values for primary, secondary voltage and the rating of transformer. Then thyristor controlled reactor and capacitors both are connected in delta. This is to eliminate the harmonics produced by the eliminate triplen harmonics, third, sixth, ninth. Because semiconductor devices, as you know, they are not exactly sinusoidally producing, but they have enough many harmonics contained. So that is connected in delta. Value of inductance and capacitor should be entered in TCR and TCAC. This is the most important. This is as per your design. And SVC controller, here you should mention the droop characteristics of the SVC. Here you should mention minimum and maximum susceptance that the SVC can provide. It is not like that it is not a generator, it is a SVC. This is not a generator. It will produce voltage as per its capacity. If all the inductance, all the capacitance are taken in the circuit, so its maximum and minimum susceptance that it can provide, and accordingly the reactive power it can provide should be mentioned, and it generates firing pulses for this. Now there are two main things that you can see here. Is one is voltage regulation and one is VAR control mode. In voltage regulation, voltage at a particular bus will be maintained, and in VAR control, reactive power will be maintained, and according to this requirement, firing pulses will be generated, and number of TCS that are to be inserted is decided by the controller. Now we will see here, this is the programmable voltage calculator. Here you need to enter the values for voltage at particular time. Amplitude, say 1 amplitude at 0, then 1.025 amplitude is at 0.1, 0.93 is at 0.4, and 1 as again 0.7 value. This is the time, this is the amplitude. ये time पे इतना value चाहिए, like that is okay. Here this is capacitor value, inductance value. Here it is inductance value because it is TCR, so that you should mention. Here it is capacitor value that you should mention as per the design. This is the controller. in controller you have two modes. One is voltage regulation, other is VAR control. That is reactive power. That is, this will give constant reactive power, and voltage regulation will provide you constant voltage, whatever you have mentioned reference. Droop characteristics should be mentioned, and here it is the minimum and maximum primary susceptance that can be provided by the SVC that you should mention. Okay. Now, once we enter these values, remaining values like transmission line parameters, that all you know, that must be entered. This is the diagram showing primary voltage, current, reactive power that is supplied. Since we are operating it in V voltage regulation, so measured value and reference value. This is the angle because thyristor controlled reactor, the reactance is controlled by the firing angle, that is alpha, and number of thyristor switched capacitors. You know that capacitor banks are either switched on or switched off. So as per the voltage programmable voltage calculator, programmable voltage source, the voltage is increased at 0.1. So this this is yellow line indicates voltage output of the programmable voltage source, which is higher than the reference. This indicates reference line. So when the voltage rises, reactor should absorb the power. So here this is alpha, that is for reactor, that is thyristor controlled reactor. So alpha is near to 144, like that. And here it is number of thyristor switched capacitors. Since voltage is increased, we do not require capacitor in the circuit. So capacitors are out of, or they are not connected. It is the reactor which is only controlling the voltage. So how it controls voltage? By absorbing the reactive power. This reactive power is negative, which is being absorbed by the thyristor controlled reactor. Then at this instant, the programmable voltage generator or source has voltage is reduced. Since voltage is reduced, it must be boosted. So capacitors banks should be made on. So how much capacitor banks are required? They are taken in the circuit one by one. So first, second, and third. With this capacitor banks, the reactive power that is supplied to the grid has increased. So this is shown by this. Again, voltage is increased. Voltage increase, voltage given by the source is increased. So it should be brought to the reference. That can be done by disconnecting the capacitors and introducing reactor in the circuit. So with that, again you will get the value as per the reference. Are you following this? This is the reference voltage. Here the voltage has increased. So increased value of voltage should be again brought back to its reference. This can be brought by absorbing the power. So power is absorbed means it is shown here negative. Power is absorbed by the inductor, that is TCR, thyristor controlled reactor. So which makes this firing angle at 140 degrees, and thyristor controlled reactor is taken into service. When the voltage is dropped, it should be again brought back to its reference. That is done by introducing capacitor banks switched in one by one. So that is shown by this, and with this there is increase in reactive power, and this continues till voltage is less, and when again voltage is greater than the reference, again same should follow, that thyristors should disconnect, or it should switch off the capacitor banks, and increased power should be absorbed, so reactor should be brought back in the circuit. So this is the way how SVC works. Depending on the loads, depending on the requirement, the value of inductance and capacitor bank should be decided. Is a fix, when it is operating at fixed VAR, it is very true that voltage or voltage should be such that it should provide fixed reactive power. Thank you. Done किया?